Now we are going to start with the third theory, that is the crystal field theory. As we have come across the many limitations faced by the Werner's theory, the valence bond theory, so now we have a theory which is just trying to explain the color, the magnetic properties and all those which were, or you can say the concepts which remain unanswered in those theories will be able to answer, we'll be getting answers from this theory. So just look at the board. So before we start with crystal field theory, I just want to remind you that you know that according to Bohr-Bury rule, we just you can say that divided the different orbitals in order of increasing energies. So there we took the sum of n plus L, and we arranged the orbitals in order of increasing energies. That is, the 1s as we know is having a smaller energy, 2s is energy of 2s is greater than 1s, 2p is greater than 2s, 3s is greater than 2p, 3p is greater than 3s, and 3d is, but what we see is that actually when we come across 3d and 4s, so the energy of 3d and 4s is almost comparable. The energy of 3d and 4s is almost comparable. So what happens in certain cases, what we found that the energy of 3d fall down and energy of 4s rises, but in certain cases what we see that energy of 4s is low and energy of 3d is high. So though they have comparable energy, so we can encounter such kind of changes when we come across the different compounds actually. So you need to keep this in mind that 3d and 4s have comparable energy. So you can find certain cases in which 3d has less energy or 4s is higher or vice versa. So just keep in mind, this is an important point before we start with this crystal field theory. So now this crystal field theory is also called as the electrostatic model. It is also called as electrostatic model because it has actually tried to explain the formation of coordination compound by use of the electrostatic force. So according to it, metal is positively charged. Metal is positively charged. And if we talk about ligands, ligands are negatively charged. So according to this theory, metals have positive charge, they are cations actually, and ligands are negatively charged, that means they are anions. And you know there is a bonding between them. And the bonding is merely due to an electrostatic force because metal is positively charged and ligand is negatively. We know that opposite charges just try to come closer. So they will come closer and they will bond with each other, and that bond is merely due to the electrostatic force of attraction because both are charged particles. So this is what crystal field theory states in its first statement, that metal is positively charged, ligand is negatively charged, and they both are bonded by an electrostatic force, right. Second thing what this suggests is, when they bond, so obviously the bond is going to be coordinate, that this is clear, like we have done in the past also, that in coordination compound strictly the bond is coordinate bond, right. So the coordinate bond, if we talk about the geometry in this case now, which geometry will be favored? That geometry will be favored which will minimize the repulsions, or you can say which has minimum energy and maximum stability. Not only in this case, we know in every compound, if we talk about geometry, every electron pair is just tend to move away from each other in order to minimize the repulsion and to get a state of minimum energy and maximum stability. You know that everything in universe is just struggling for the stability, right. So as the same as coordination compounds are doing. And you know that see, before starting this point, I would like to tell you one thing. You know that d subshell actually has 5 orbitals. You know that. 5 orbitals, that means maximum electrons that it can accommodate is 10. And if we talk about the name of the orbitals, we have this, I have already drawn for you. We have dxy, dyz, dzx, dx square minus y square and dz square. This you have already done in chemical bonding. So as if we talk about the energy of these 5 orbitals, so they are degenerate orbitals. We know that they are degenerate orbitals. What do I mean by saying the term degenerate? It means that they possess the same energy, So though they possess the same energy, but still you know what happened, when the ligand approach towards the metal atom, this degeneracy actually breaks. This degeneracy actually breaks. But this degeneracy is lost only when the ligands approach the metal atom. Otherwise, when we talk about the d orbital, all orbitals are of same energy, they are degenerate. But as the ligand atom just approach towards it, the metal atom, in order to bond with it, the degeneracy actually gets lost, or you can say the orbitals now possess the different energy. So now out of these 5 orbitals, which orbitals are going to possess higher or less energy? So just look at the board. Energy of xy, yz and zx, probably these ones, right? Their energy is somehow similar to each other, and the energies of dx square minus y square and dz square is again the same one. So what we do is we call this energy, or we indicate their energy by T2G. We indicate their energy by T2G, and as far as their energy is concerned, we write it by, or we abbreviate by writing Eg. So that means these are going to possess different energies, and dx square minus y square and dz square is going to possess different energy. Their energy is indicated by T2G and their energy is indicated by Eg, right? So there is a gap actually. So now just look at the third point. So it states that in presence of ligands, d orbitals split into 2 cases. Now I think it's clear why they split. They split because their degeneracy gets lost and they get splitted into 2 cases depending upon their energies. So as I told you, x, y, yz and zx is going to possess T2G energy, and dx square minus y square and z square is going to possess energy equal to Eg. So that means degeneracy is lost, right? Then you know that ligands which approach, they actually can produce a strong field splitting, or you can say they are called as strong field ligands, or they are called as weak field ligands. If they are able to create a lot of energy difference between the orbitals, they are strong field ligands. And if they are able to create less difference, they are called as weak field ligands. And just look at the board. I'm trying to explain it with the help of graph. See, I have, let's say my molecule possess this much energy, because we know that every molecule has certain amount of energy. So let's say that the metal atom possess this much energy, already possessed by it. Now I'm going to add ligands to it. So when I add ligands to it, its energy rises, and it rises to a maximum, and then it get actually splitted. Then the energy gets splitted. So let's say that this energy, if it is T2G and this is Eg, so that means there is a gap between T2G and Eg. So now depending upon that which ligand is present, so it can we can actually talk about that it is a strong field ligand or a weak field ligand. If it is able to create a lot of energy difference between it, it is a strong field ligand. And if it is able to create a small energy difference, it is called as weak field ligand. So depending upon the crystal field splitting, this is actually crystal field splitting. So what is crystal field splitting? If somebody asks you about the definition, it is the split of d orbitals according to the energies on the approach of ligand into 2 cases is crystal field splitting. What is that? It is the splitting of d orbital into 2 cases, or you can say into T2G and Eg when the ligand approach it, right? So that is called as crystal field splitting. So just depending upon the extent of crystal field splitting, or depending upon the magnitude of crystal field splitting, that how much it can create energy difference, we classify the ligands into strong field ligands and the weak field ligands. If they are able to create a lot of difference, they are strong field ligands. If they are able to create a small difference, they are called as weak field ligands. So this is the spectrochemical series in which I have just arranged the ligands in order of their magnitude of crystal field splitting. So that means this iodide ion can produce less crystal field splitting, that means it creates less energy difference. And if we talk about this carbonyl, it is the one which create a maximum crystal field, or you can say can do a maximum crystal field splitting. So this is how we can arrange the ligands according to their magnitude of crystal field splitting, and it is probably called as spectrochemical series. Spectrochemical series, right? So I think it's clear that d orbital, they have same energy, but when the ligands approach, their energy gets splitted. The split can be this thing also, that suppose this is my dxy, yz and zx, they possess higher energy, and my x square minus y square and z square possess lower energy. It may happen, or it may happen like that the splitting occur this way, that this is my Eg having higher energy, and my T2G is possessing a lower energy. So anything can happen, it just depends upon that which ligand is approaching the metal atom. It just depends actually on that, right. So that means splitting can occur in either case. It's not like that if in every time T2G is going to get higher energy or EG is going to possess, no, it's not like that, right. Keep in mind, it is just the nature of the ligand which you can say which abruptly increase or decrease the energies of the orbitals, right. So this is what the theory says. Now when the ligands approach, they break into two parts, as I've already told you that they get broken up, degeneracy is lost, some orbitals possess higher energy, T2G may have higher, EG have less, or EG have less, or T2G have higher. You know that why I'm telling you that T2G has sometimes higher energy or EG has lower energy. You know that how it depends actually. See, it is actually apart from your syllabus, but still I just want you to know that why some orbitals have high energy in certain cases and the energy falls in certain cases. It is just the method that from which side the ligand is coming. See, if I have this dxy, I say that my ligand is coming from this side. Let us suppose, right, my ligand is entering from this axis, let's say from this axis, right. So when it enters from this side, so because the electron clouds are between x and y, so that means they will suffer less repulsion, right. And in this case again, if they enter from this side, they will suffer less repulsion because they are present between y and z axis. Similarly in this case, but if my ligand enter from this side, it will suffer more repulsion because my electron cloud is on the same axis. More repulsion means more energy and less stability. So that means in similar way, if my ligand enters again from this axis, it is going to suffer high repulsions, and high repulsion means high energy means less stability. So in these kind of things, the dx square minus y square and d square z square is going to possess higher energy as compared to these, because they are actually offering less repulsion depending upon that from which place the ligand is entering. So this is just the concept that what is the nature of the ligand and from which side it is just trying to enter. Does it suffer more repulsion or it suffer less repulsion? According to that, we just classify the energy as higher or less energy. So this is what crystal field theory just tries to explain. Now we'll just take up an example in order to explain you that how the crystal field splitting occur in octahedral and the tetrahedral type. So just look at the board.